Welcome to this lecture of microscale transport process. The topic that we would like to discuss today is this plastic microfluidic devices. You have already understood that there are certain methods to manufacture these plastic devices by the use of a mold. So, there are three techniques we talked about. One is casting, another is molding, another is micro injection. Now, I basically in previous lectures I discussed this process just as a technique. I mean, you have a mold, you have a liquid, you have a polymeric, you have that plastic material above its glass transition temperature, and you pour it, and then after some time you take the negative part of it, and that serves as microfluidic device. And there are methods how to do the casting and micro injection. We have discussed this in detail. What I would like to do today is I would like to discuss the theories, the physics that controls this process. It's not like, I mean, just you pour something and it will automatically happen. There are certain physics. For example, the capillary force, which is instrumental in taking that plastic melt, plastic melt to go inside those structures. So, these are extremely important. So, you need to understand that there are certain physics which you need to consider if you want to make a plastic, if you make successfully a plastic microfluidic device. So, my intent in today's class is to at least touch upon those issues in physics which you need to know to handle this manufacturing of plastic microfluidic devices better. Let us see what we have here. So, what you have here is basically you are having, I mean, first of all I say that what we are talking about here is patterning by natural force, such as capillary action. Okay. Why we are saying this is that the mold with relief features. What is relief feature? Relief feature is that those, for example, you want to make a channel. So, there is, I mean, the negative part of it would be that there would be a raised portion, right. So, there are relief features, or if you want a raised portion in the microfluidic device, for that you are supposed to have a channel in the negative part. So, the mold with relief features when placed on a fluid, okay, or solid surface. You may say, why am I placing it on the fluid, because I thought we are pouring the fluid on this. Probably what I am talking about here is you have a substrate which is flat, then you have a mold. This is the mold. Okay. So, you bring this mold, bring in contact with this substrate, okay, and then you put molten polymer into one of these channels. So, this is brought in contact with this. So, there is no spacing here. So, they are in contact, and then you are pouring the liquid at one end, and you will see that by capillary action it goes everywhere. This is the third dimension, all right. So, these channels also have third dimension. So, you got my point, what I am trying to say. So, the mold with relief features. So, these are the relief features when placed on a fluid or solid surface. The space between the mold, and the surface creates network of capillaries. Network of capillaries. You understand what I am talking about? I mean, then this would be so this spacing is gone. So, basically so if I advance this substrate, so this is the place where the substrate is. So, this is the place where the substrate is now. So, so then these would be forming. So, all these channels or the raised places, they will form a network of capillaries, if you will, but if we introduce polymer at one end of the channel. So, there are network of capillaries, this you understand. Now, this network of capillaries, there are three possibilities. One is open ended, second possibility is closed, and the third possibility is closed permeable. I mean, closed, though it is permeable. What I mean by this is open ended means, let us see first what happens if you have a closed capillary. You have a network of capillary, you had a mold. So, this mold has a third dimension here. So, you are bringing this mold in contact with another flat substrate. So, you have formed a network of capillary, and then you are introducing the fluid, that means that molten polymer above its glass transition temperature, which is in its very viscous liquid state. You pour that here and you expect that it will go everywhere by capillary action. Now, if this capillary is open ended, that means if you have an opening here open to atmosphere. So, you will at least make sure one thing, that is that the air that is inside, because it is originally filled with air, right, when you introduce the liquid, that air need not get compressed. So, when as the fluid moves in, fluid can move in everywhere and the air can go out, because these are all connected. Okay, connected network of capillaries. So, air can go out. So, you don't have a problem of compressing the air. So, this is one issue here. The second is closed one, that means you do not have any air outlet. So, it is all closed except the end through which you have introduced the polymer, that liquid polymer at above its glass transition temperature. So, in that case you will consider these to be closed. So, in that case, if by capillary action you are if the capillary action is pushing that liquid, but still air is getting compressed, you need to understand this. And the third type is closed permeable. You know that certain polymers, they are permeable, they can allow air or vapor to pass through it. There are various mechanisms. It is like the students who have studied membranes, they will appreciate it, that it will not be that this material is porous. What will happen is certain vapor will get dissolved in the polymer and then it will go out from the other end. So, there are various mechanisms possible. It is not just that it is physically there are holes and through holes the air is passing out. It is an intact polymer, but suppose the I mean, why I am talking about vapor is lot of times you may not melt it. I mean, I am talking about a molten, I am talking about a polymer melt, but it could very well be possible that you do not melt it, you add certain solvent by which that polymer becomes, the polymer dissolves in that solvent and it becomes liquid, and if you can somehow get rid of that solvent, then polymer will go back to its own state. So, that is a possibility. So, if you are using that method, then if you can somehow allow the solvent to go out of the system, that is all you need. Okay, it is not air. And if that solvent, if the microfluidic device, the plastic material that you are using allow the solvent, if that allows the solvent to go through it, allowing the solvent means that solvent will dissolve. So, if this is the layer, if this is the plastic layer, solvent will dissolve in this material and then permeate through it, okay, and then it goes out through the other end. It is not that you have a predetermined pore present through which it is traveling. It is a complex mechanism. I mean, it's not it's a physico-chemical mechanism, not exactly a physical mechanism by which this transfer may take place. So, you have another category which goes by the name closed permeable. Okay, so, these are the three possibilities that exist. Now, couple of things we need to know at this point. One is a polymeric material becomes fluid like number one, when heated above its glass transition temperature. When heated above its glass transition temperature. Now, you may ask, what is the glass transition temperature for various polymeric material? It is listed and you have access to it. Probably to get some order, if you want to know what is the order of these glass transition temperature for common materials, it is of the order of 100 degree centigrade. So, actual values you need to it varies. So, polymeric material becomes fluid like when heated above its glass transition temperature or through the action of a solvent. That means, if you bring that through the action of a solvent, that means, if you dissolve the polymer, if you put the polymer inside a solvent, there is a possibility that the polymer will melt, which we have seen in our day to day life. There are solvents in which this polymer is dipped. Now, when we are talking about this patterning, when you are talking about this filling of capillaries, this network of capillaries by polymer, if we try to articulate it in the terms of this microfluidic manufacturing, it would be like this, that liquid fills the mold by capillary rise. Rise is not, by capillary action would be probably the right word, that by capillary action after the liquid fills the capillaries, it is solidified by two ways. One is by thermal method. Thermally means it was above glass transition temperature, now you simply cool it. So, it is automatically it will solidify, or by exposure to UV light. Lot of times it is a pre-polymer, you have all the ingredients, but the solidification process is initiated once you expose that polymer to UV light. So, that is also another possibility, and once this is solidified, then what you do is you go for removal of the mold. So, the mold is removed. Okay. So, what you have is you have a choice of thermally doing it, that means cooling it basically, or by exposure to UV light if you have if you have the polymerization to get complete and UV light happens to be the agent to accomplish that, or if you have dissolved the polymer in a solvent, then you have to make sure that the solvent is evaporated. that is probably the third choice you have, solvent. Solvent is evaporated. Okay. So, if we talk about this patterning by natural or patterning by capillary action or filling of this mold by capillary action, this is something which you are actually doing. Okay. So, these probably you understand. Now, there is another force other than the capillary force which can also be used for patterning, but this is probably done when the feature size is smaller. That is the use of van der Waals force. In these terminologies in my people working in this area, this is also referred as London force. Okay, the point here is that this force is large when the film thickness is small. What film we are talking about here? If you have a substrate, on top of that you have a film. Okay. If the film thickness is small, then this force becomes significant. Okay. In fact, there is a dependence which is non-linear. So, more the film becomes thin, this force increases in a non-linear manner. So, when it is large, the film thickness is this becomes large when film thickness is small, and what that means is that when film thickness is small enough, okay, when film thickness is small enough, the film will break into islands by a process referred as de-weighting, and this implies exposure of substrate surface between the islands. That means this film will start breaking. Into islands, and between these islands the substrate surface is getting exposed. So, this film is breaking. All right. The de-weighting phenomena, these phenomena is used to fill, sub-micrometer channels. When the feature size is smaller. So, the de-weighting phenomena for thin polymer films, by thin I mean less than say 100 nanometer on solid surface undergo de-weighting when taken above. These thin polymer films, this is common, that thin polymer films of this dimension, they undergo de-weighting. These undergo de-weighting when taken above glass transition temperature. So, what this means is, if you can first form a thin polymer film and then heat it above its glass transition temperature, you will see these islands being formed. Okay. Initially, of course, this process is much more complex than the way I am presenting it, but I just wanted you to appreciate that there is such method existing. Make sure that don't have any confusion here. Initially cylindrical holes are created. Basically, cylindrical holes means if this is the surface, you will see this portion, the substrate is getting exposed like this, and initially cylindrical holes are created in the film, and as the holes grow, the basically as the holes grow, you have a rim here. It forms a rim, and these rims they come in contact with each other. And then they form, instead of holes, you will see droplets existing in between phase. So, these holes, it has grown, and so at a grown up state. So, first a cylindrical holes will appear, and then you will see that these would be forming. So, these holes are there. Basically, instead of holes, the pattern becomes that you have a droplet here, you have a droplet there, you have a droplet there, you have a droplet there, and rest of the part is all blank. So, if somebody requires such feature, in the on the microfluidic surface, he can the person can utilize these force as well. That is what I am trying to convey. All right. Now, let us so with this background. So, I have basically choice of, one is capillary action, which we have talked about, and I said there are these various methods possible, and I said that there is also existing another alternative method which goes by the name which is basically this use of van der Waals force, and this is applicable for features which are probably sub micrometer scale. Now, let us talk about these open-ended capillary, because we said, I mean, I will be focusing on these capillary action here in today's class. So, we talked about these three methods: open-ended, closed and closed permeable. Let us see how it would appear if we want to focus on the open-ended capillary. Open-ended capillary, it is, let us say we are talking about capillary filling of a pre-polymer. I mean, pre-polymer means you expose it to UV, you expect that the polymer it will solidify. Capillary filling of a pre-polymer in Pdms mold. So, here the mold is made of Pdms. You know the Pdms material. Pdms material is used for making of microfluidic device, but here I am talking about the mold that you are using, that is made of Pdms. You understand that is highly possible. So, Pdms mold so capillary filling of a pre-polymer in PDMS mold. Now, if one drop is placed in one end and the capillary action takes the pre-polymer to other end of the channel, then based on Poiseuille's equation, if V is filled liquid volume, okay, then and T is time. So, dV dt, the rate of change of filled liquid volume, what would that be? That would be the velocity multiplied by the area, that would be equal to pi r to the power 4 rho divided by 8 mu z. What is now these terms? Mu is equal to viscosity of this liquid, viscosity of liquid, T is time, R is equal to radius of capillary, and Z is equal to distance to which liquid fills the capillary. Okay, so, if these are the terms, then you can write using Poiseuille's equation that rate of change of filled liquid volume dV dt is this quantity, and on top of this I think this should be P, right? P, delta P. Okay, so this is probably this should be P, or I can say this is delta P. Yes, delta P. Fine. Now if we try to write the if the driving force for the filling is Laplace pressure, then you can write this P to be equal to, or this delta P to be equal to 2 sigma cos theta, if you have this should be included, divided by R. So, in that case you can write dz dt, that is equal to, from this, R sigma cos theta divided by 4 mu z, and then you have V is equal to here, because this is happening because V is equal to pi r square z, that is what you are using. So, if that is so, you get z is equal to r sigma cos theta divided by 2 mu to the power half t to the power half. So, this gives you the distance that you would be traveling, that the distance, that z is distance to which liquid fills the capillary as a function of time. So, if one is interested to know how far say at a given time how far this prepolymer will travel inside the PDMS mold, this can be figured out from this equation. One thing I would like you to appreciate here is that the distance to which capillary filling occurs becomes smaller distance to which capillary filling occurs becomes smaller if capillary size goes down, if surface tension goes down, if contact angle goes down. So, you want them to be up, so that you can have a faster feeling, and viscosity probably you do not have much control, because it is the prepolymer that you have here. So, anyway for the viscosity it is inversely related. So, that dependence you can see here. And the other aspect is this, whether to use whether it should be an equilibrium contact angle or a dynamic contact angle, that also, that point is also there, which can be looked into. Now, instead of so we talked about this open ended capillary, and we have some understanding at what rate it will be filled and everything. If somebody is working with a completely closed capillary, completely closed capillary, what I mean by completely closed capillary is that you have, suppose this is a feature we have, and you want and you have put it, this is the substrate, and you are having a feature and it is completely closed. I should not be putting it here this way, probably let us draw it again. You have a completely closed capillary. So, this is the feature you have, and here you are expecting that so there is a gap through which the liquid is penetrating here. Now, by capillary action, the fluid tends to go up this way. So, maybe it has gone up to this level. So, this is the level up to which the liquid could fill. However, the air that is there, this air is getting compressed. So, you have a air pressure here. So, what I mean is that this capillary by capillary action liquid will tend to fill this channel. However, by doing that it is compressing the air which is there, because air has no outlet. So, what will happen is, so this is the case when an impermeable mold is placed on polymer surface. Let us say, so that is what I am saying, this we have to assume that there is polymer. Okay. So, here we have the polymer, and maybe you have the substrate down there. So, you have the polymer should come in and go inside there. So, impermeable mold is placed on the polymer surface, air pressure will build up, I mean that you have already understood in a closed capillary. So, this air pressure impedes capillary action. Now, one thing you got to understand, that at the beginning this entire channel, the air pressure was atmosphere. So, if somebody wants to say let us say this height is z, or let us say this height is say h, capital H, okay, and let us say this level is say z. So, basically capillary rise has taken place at atmospheric pressure to a height z in a capillary of depth h. Let me write it again. Capillary rise took place at atmospheric pressure to height z in a capillary of depth h. Okay. So, the pressure of the trapped air in the capillary is what? If we the area remains same, so it is the volume, and if we assume that the pressure multiplied by the volume remains same. So, what would be the new air pressure? If P 0 is equal to initial air pressure, which for all practical purposes would be 1 bar, P 0 is initial air pressure, then you can say that the final air pressure would be equal to P 0 into H divided by H minus Z, all right, or you can write this as P 0 divided by 1 minus say Z prime, where Z prime is equal to Z divided by H. Now, we are interested in knowing what is Z by H, what is Z prime for that matter, how far capillary can go. Again, capillary rise also has a limitation. So, how far it can go compressing this air, because if you see that the 90% got filled, 90% of this volume gets filled. So, you will assume, okay, I started with a feature size and then I got 90% of it. So, you better have your feature a little higher and have this done. So, our thought process works that way. So, if it is that way, then the capillary rise. So, one thing you can write here is that the capillary rise will cease. Capillary rise will cease when this final air pressure is equal to Laplace pressure. So, if that is so, then you can equate this with the Laplace pressure, which is equal to then 2 sigma cos theta divided by r. So, then you can come up with this z prime as equal to or you can write, if this is the, if you write this as P L, then you can write z prime as, tell me if I am wrong here, I can possibly write P L divided by P 0, that can be written probably. Z prime, so 1 minus z prime would be P 0 by P L, or 1 by P L minus, yeah, I can write it, right. So, this is so if you know the Laplace pressure, if you know, so if this is atmospheric pressure, so you can come up with what would be this z prime. Now, you need to understand couple of things here, is that no capillary rise will take place if Laplace pressure is less than 1 bar, less than atmospheric pressure. If it is less than atmospheric pressure, no capillary rise will take place. That is one issue here. Second point is that Laplace pressure increases with capillary size, with capillary radius decreasing. Okay. So, that means decreasing feature size, what this means is decreasing feature size can ensure P L is greater than P 0. Now, one thing I would like to then point out, then if you have a variable feature size, then so you can expect rise also would be variable. That is another issue here. So, that needs to be looked into as well. Okay. There is another point which I need to make here, is that why I started I started talking about this Pdms mold. Pdms mold, I mean that means this, by mold I mean this. So, this material is made of Pdms. Okay. It has certain purpose. I mean, if you have this, if this mold is made of Pdms, basically what you need is, I mean, you have a choice of hard mold or you have a choice of soft mold, or hard mold. If you have a choice of hard mold plus hard substrate, okay. And or in other words, you can have, and I do not want to call this soft mold, a flexible, little flexible mold, not very flexible, but some flexibility that is actually required. That is why I have mentioned there, it is Pdms mold, because these amount of flexibility, certain amount of flexibility is required. I can tell you why. I mean, from fundamental standpoint, you are talking about a substrate. This is a substrate, and then you have this mold. They are coming in contact with each other, right? So, this is made of PDMS. This material is made of PDMS. Now, you have to make sure that the contact between this mold and this substrate, that contact has to be good. If there is, so everything has they have a roughness, right? This one has a roughness, the upper one has a roughness, the bottom one has a roughness. So, when you are bringing them in contact with each other, you have to make sure that they are contacting with each other. Otherwise, they could be I mean, you may not be satisfying all these requirements of contact angle. I mean, you are saying, okay, this is the contact angle that you have and that contact angle you are using, but if your upper one is like this, the bottom one is like this, and they are not contacting with each other, and then you are having the liquid. So, if your calculation is based on that, then there could be trouble. So, soft mold will at least no. So, you can achieve a what we call conformal contact. You can achieve by pressing them hard. That is possible. I mean, always you can press them hard, so that they make a conformal contact. However, if you press them hard, I mean, if you are ready to put that much of exercise on this, then you may as well squeeze the liquid into it instead of depending on the polymeric on the capillary phenomena to go everywhere. You can just squeeze it. So, these particular issue you need to understand, that this slight roughness or uneven layout on the mold will go against, this will go against the perfect weighting of capillary wall. So, you need, the choice is, you need high pressure to bring them in contact, high pressure to bring them in contact, but then probably this capillary filling by capillary action becomes inconsequential, because if you are really employing high pressure, then you may as well use the squeezing to have this material travel. So, so flexibility in the mold itself has some benefit, some amount of flexibility should be there to bring this contact. There is, so the third point, I mean, so we have talked about open, we have talked about closed, and the third point was when you have this permeation, when there is a possibility that some part can permeate through the wall of that mold. So, we are talking about closed permeable capillary. This is the third point. Now, in closed permeable capillary, this is first accomplished by solvent assisted molding. What is that? Pdms mold is weighted PDMS mold is weighted with a solvent and then is brought into contact with the surface of the polymer. You can see what we are doing here, we just reversed it. PDMS mold is weighted with a solvent and then is brought into contact with the polymer, and that polymer is supposed to be dissolved in that solvent. That is the idea. So, while in contact the solvent dissolves a thin layer of polymer and this polymer solution conforms to the solvent dissolves a thin layer of polymer and this polymer solution conforms to the surface topology of the mold by capillarity. So, basically this solvent dissolves a thin layer of polymer and this polymer solution will conform to the surface topology. So, while in contact the solvent dissolves a thin layer of polymer and this polymer solution would be now traveling to the nook and cranny of this the features by capillary action. So, this is a possibility. Next, the solvent permeates by the mechanism that we said and polymer solution solidifies. So, polymer solidifies. Solvent permeates and polymer solidifies. So, that is basically this is what you call solvent assisted molding. This is probably this is given the name solvent assisted molding. There is another possibility another possibility is there that after the spin coating, immediately after the spin coating, immediately after the film is formed by spin coating. What do you do after spin coating? You generally you have that liquid part evaporated, right. So, you put it after the spin coating, you put it in oven or you let it dry. So, immediately after the film, when still it is wet, it has not been evaporated. At that state, if you can bring the mold and put it on top, so that is also another possibility. So, you have a thin film and so you have when it comes to closed permeable capillary, you have one is solvent assisted molding, where you have the polymer which is solid, but PDMS mold that you have is on the surface you have that solvent and you bring in contact, you bring that, and wherever it touches the polymer, that those portions polymer gets softened or polymer gets dissolved, and that liquid that forms that will flow through the nook and cranny of those features using capillary phenomena. That is one possibility. Other possibility is that you have spin coated the polymer and the polymer still contains it has not the liquid part has not, that solvent part has not been evaporated, the solvent is still there, and now you bring in the mold and put it on top. So, then also you expect that with the solvent that that polymer will enter into the features by same capillary action, and the same process will continue. So, this is also this is the second method by which you can go for this closed permeable capillary filling. So, now probably you understand that this, if somebody is interested in filling the micro features, these are the three possibilities they have, and these are probably, I mean, I just want you from this lecture, what I want you to do is, I want you to appreciate that there is substantial amount of physics involved, and you need to be sensitive to these theories while designing your fabrication process. It is not just some empirical cooking. I mean, it has a lot of physics behind this, and of course, one can utilize the van der Waals force if somebody wants to go for feature size below micrometer scale, and how it works out. I have already talked about that. If you have a thin film and more you get, it becomes thin. So, you have a thin polymer film and then you heat it, and then you see that the features are forming, and then at one point you will see that simply you are left with some droplets present on the substrate. So, if that is something which you are looking for, you can probably make use of these processes to your advantage. So, that is all I have as far as today's class is concerned. Thank you very much.